Okay, good morning, everybody. Welcome to my talk about how JSR-385 could have saved the Mars Climate Orbiter. My name is Filip, and I'm a contributor to the JSR. Let me start by telling you the story of the Mars Climate Orbiter. It was launched on the 11th of December 1998 at 18:45 UTC, so that's your time actually. And it was launched from Cape Canaveral aboard a Delta II launch vehicle. The complete burn sequence lasted 42 minutes and brought the spacecraft into a so-called Hohmann transfer orbit from Earth to Mars. And the orbit is 669 million kilometers long and takes 9.5 months to complete. So that's a little bit over a pregnancy. The primary science objectives of the mission included to determine the distribution of water on Mars, to monitor the daily weather and atmospheric conditions, to record changes on the Martian surface due to wind and other atmospheric effects, to determine temperature profiles of the atmosphere, to monitor water vapor and dust content of the atmosphere, and to look for evidence of past climate change. So that's a whole set of things that the Mars Climate Orbiter was supposed to do. However, this is the entire result of the mission. This picture costed $125 million. And it was taken on the 7th of September 1999, 16 days before the Mars Climate Orbiter would have encountered with Mars. So, the Mars Climate Orbiter began its planned orbital insertion maneuver on the 23rd of September 1999 at 9 hours and 45 seconds UTC. A week earlier, it executed trajectory correction maneuver 4, and the intent of TCM-4 was to bring the Mars Climate Orbiter into a trajectory which would have put it 226 kilometers above the surface of Mars. However, during the week between TCM-4 and the ultimate orbital insertion maneuver, the navigation team got indications that the spacecraft in reality was headed for an orbit much lower, namely 150 to 170 kilometers above the surface. 24 hours before the orbital insertion, new calculations placed the orbit at an altitude of 110 kilometers. And the minimum altitude to survive was 80 kilometers. So you see, it goes down from 226 to 150 to 110. And there was a meeting held to consider a TCM-5. All the attendees agreed there should be a TCM-5. A new correction maneuver, but somehow it never was executed. So the Mars Climate Orbiter was supposed to go out of radio contact when it passes behind Mars, and that should have been at 9 hours, 5 minutes and 41 seconds UTC on the 23rd of September, but communication stopped 42 seconds earlier. And they did some calculations of what really happened, and they found out that in reality, it probably went into a trajectory which would have been 57 kilometers above the surface of Mars. That means that it probably just disintegrated in the atmosphere and disappeared. So what went wrong? The primary cause was that a piece of software provided by Lockheed Martin produced results for the total impulse by the thruster firings in pound force seconds, whereas the trajectory calculation software provided by NASA expected it to be in Newton seconds. The software specification said it should have been Newton seconds. So Lockheed Martin clearly made a mistake. However, NASA couldn't put the blame on Lockheed Martin because their checks and tests should have discovered long before the launch that there was a problem. Interestingly, there were at least 2 navigators who noticed that there was something wrong between what was calculated and what was actually measured as a position of the Mars Climate Orbiter, and they filed a report, both of them. Had it been 2019, they would have submitted a JIRA ticket. And their concerns were dismissed because they did not follow the rules about filling out a form to document their concerns. So in 2019 terms, they didn't check the effects version field in the JIRA ticket. So this is a quote from Edward Wheeler, the NASA Associate Administrator for Space Science, and this is what he says: "The problem here was not the error, it was the failure of NASA's systems engineering and the checks and balances in our processes to detect the error. That's why we lost the spacecraft." So, lessons learned. Read the software specifications. If Lockheed Martin had done a good job, it would never have happened. Use JSR-385 instead of primitives. Again, that would have saved the Mars Climate Orbiter. Also an important lesson, don't leave it to the checks and balances to discover problems. Make sure that the problems never occur to start with. You can't rely on your testing regime to figure out all the bugs. And don't rely on bug reports from users because they may be dismissed on formal grounds. Now, this is of course not the only mishap. There is the famous 12th of October 1492 mishap. Columbus miscalculated the circumference of the Earth because he used Roman miles instead of nautical miles. And so when he ended up in the Bahamas, he thought he was in Asia. Consequence of that mishap is that the Native Americans were called for Indians 500 years afterwards. Then there is the Gimli glider in 1983. This happened just after Canada went over from imperial units to SI, the SI system. What happened there is that the captain of the flight, he has the responsibility to calculate how much fuel he needs. So he did all the calculations, and what happens then is that the ground personnel has to do the calculations too, to verify that the captain didn't make a mistake. So the captain gave his results to the ground personnel, and they did the same calculation, and they came to the same conclusion about how much fuel they would need. The problem here is that the captain made a mistake in the conversion of the units, and when he gave his results to the ground personnel for the verification of the calculation, the ground personnel used the same conversion factor. So instead of looking it up independently, they reused the factor that the captain had used. And they came, of course, to the same result. So they got less than half of the fuel needed. So halfway in the flight, the airplane went out of fuel and the engines stopped running. Luckily, there was an airport not far away from where that happened. It wasn't in operation anymore, so it was used for car races and festivals and all sorts of happenings. And actually on that day there was a festival going on there with children and people playing and barbecuing and everything. So what normally happens is when a plane comes down, it went sliding down to the airstrip. Normally a plane makes a lot of noise, except when the engines are off because there's the fuel. So it was perfectly silent. So you can imagine there were people running on the strip, and suddenly there is an airplane turning up from the blue sky without any sound. So it's a wonder that nobody got a heart attack of a plane just suddenly coming there. So I think only a couple of the passengers had some minor injuries from things not going entirely smooth, but nobody died and nobody was seriously injured. So it's unbelievable how much luck they had that day. Then there is Clarence the Tortoise in 2001. The LA Zoo had a tortoise, a Galapagos tortoise, that they were going to lend to Moore Park College. So they called Moore Park College and say, yeah, we're going to send it over. It weighs 250. I forgot to say kilograms. So Moore Park College built a cage because of the big tortoise, and they built one for a 250-pound tortoise. So the tortoise comes in, gets some food and water and everything, and the guards go home. So what happened during the night is that the tortoise won over the cage. And then there is a whole set of medication dose errors. When you read them, you wonder what human people think, because some of those units that we use for medication are just begging for mistakes, like teaspoon. A teaspoon is actually a defined unit, except that everybody has at home at least 5 teaspoons with different volumes. So what do you expect? The other thing is there is something like a gram, like the kilogram and the gram, but also a grain. So just saying somebody, you need to take 5 grains begs to be understood as 5 grams. So there are a lot of medication dose errors, sometimes maybe not having big consequences, but some people have died because of misunderstandings and miscalculations. Okay, so what's the problem? Primitive Java types are primitive types. And that's true in general. Primitive C++ types are also primitive types. So they can be used as building blocks for other types, but when you want to represent a quantity, you should not use a primitive type. And even if you call the constant or the attribute or the property, whatever you want, c, or speed of light, of even speed of light in kilometers per hour, it's still a primitive. And if you ask me, using a primitive to represent a quantity is fundamentally in conflict with OOP and DDD, because you're using a type representing just a number to represent a quantity which has a unit. What it should be is at the bottom that you define a quantity as a speed, so it's actually built into the property, in the definition of it, that it is a speed, and that it contains not just the number, the value, but also the unit in which it is expressed. So there is no way to misinterpret the speed of light at the bottom here as that number in kilometers per hour. So, okay, if we want to do it properly, maybe we should just define our own library. I mean, how difficult can it be? It's just a number and a unit. Except that's, of course, a lot of work because there are many units, and you will spend a lot of time just developing all the things you have to cater for. You have to maintain it, and there will be upgrades and requests for extensions, because you start with, say, a meter, and then you have to add time units, and then you have to add electrical resistance for some reason, and suddenly you have to do temperatures, and you have to be able to divide and multiply and do whatever with it. So it starts easy, but it becomes gradually more difficult and difficult, and there will be errors. But maybe the most important question is, are you a units of measurement domain expert? So even if you use the SI system every day, do you really understand how it works? And to be honest, I didn't even pose that question to myself when I started contributing to JSR-385. But right now I can say I'm not a domain expert at all. And I will be surprised, there may be exceptions, that you know all the peculiarities around SI, because there are a number of strange things, even though it is designed as the rational system as compared to some other systems. I have a lot of examples showing you what kind of strange things we have in the SI system. A quick word about JSR-385. Yeah, you can find another version of this slide deck at SlideShare if you want to have a look at it afterwards. The description is that it is a major evolution of the Unit API 1.0 from JSR-363, and it was the first one defining a set of packages to work with measurement values and quantities and units. And JSR-385 is focused on this SI system redefinition, which is going to happen in May, and also to support modularity and support for Java SE 8, 9, and above. So the basic concepts are dimensions, units, and quantities. So dimensions, that's like a length, a unit, that's a meter, and a quantity is 5 meters. But in addition, you have prefixes like kilo and milli and centi and all that stuff. You need converters, so you can go from, for example, kilometers per hour to miles per hour, or miles per second, or whatever. You need to deal with formatting, so both to print out the quantity on a unit, but also to parse a quantity on a unit. And then you have to be able to handle system of units. So for example, SI system or imperial system or Roman system if you need the Roman system of units for some reason. And to be able to handle it in a okay way. So I've set up an exercise. So we can go through the code and see how JSR-385, how you can use it to set up quantities and units and handle them in a good way. And a typical exercise, if you're working with units of measurement, is calculating the BMI of a person. And the BMI is defined as the body mass divided by the square of the body height, and universally expressed in units of kilogram per square meter. So actually, there is already a funny thing over here that it matters for the BMI index to express the units as kilogram and meters, and not centimeters, for example. We'll see as we go through the exercise that you can actually handle that in a good way, so that doesn't matter what the user is inputting, if the user is using grams or kilograms or centimeters or anything else, that you can gracefully handle and get the correct result. So if you want to set up a Java project, you can just include this dependency. Indra is a reference implementation of the specification, so you can use it and it will do the basic stuff, but it doesn't do some kinds of optimizations that one could think of would be nice to have. And currently the version is 2.0 EDR, which is the early draft revision. And I have the source code made available on GitHub, so if you want to look at it later on, you can find it there. So let's start by defining a number of quantities and just trying to print them out. The definition of a physical quantity is that it is a physical property of a phenomenon, body, or substance, and that can be quantified by a measurement. So it has to be possible to actually quantify it with a number and a unit. Yeah. So for example, the speed of light, there you have a number, the value, and the unit, for example, meter per second. And it's important to know that the same physical quantity can be represented equivalently in many unit systems. So that means that, for example, 5 meters is the same as 500 centimeters. Or the speed of light with those two representations. So the little exercise that I had was to just define, for example, the mass and the length of a person and just print them out. And then useful classes would be a quantities class where you can call the getQuantity method. And then you can use other classes like units where you have the units defined, and for example, the quantity class where you have the mass quantity defined, so they can use them and have everything properly typed in Java. So let's see over here. So taking myself as an example, what you do is just set up a mass and a height, and just call getQuantity on the quantities class, and set up 80 and units, for example, kilogram. And then we can just print it out and see that it works. So that works fine. The 80 kilograms comes out fine, and the 1 meter 89 comes also out fine. Now, you see, this is not so difficult to do. So instead of defining, for example, in an integer to hold 80 as the mass, that's not much of a simplification compared to this. It's just one line, and it explains much better what it really is than just 80 floating around in your system. Now let's go a bit further. Divide the mass by the square of the height, and then we would actually have the BMI index of a person. So let's see how that works out. There are two ways to do it. For example, the mass divided by the height, and then divided one more time by the height. And we can print it out as the first version of the BMI, or you can multiply the height with the height and then use that as a divisor of the mass. There you go. 22.4 kilogram per square meter. You see that automatically the unit in kilograms per square meter is calculated by the library. So no need to specify somewhere in the Java doc that mass is expressed in kilograms and the length in meters or anything. Everything is taken care of. You just need a mass quantity and a length quantity, and you can do the calculation without any trouble. And you can, of course, parse the mass and the height from a string. For example, if you're reading it from another system, from a file, or maybe the user is typing it in with key J or something else. And then you can see if I just use the getQuantity method with a string, it will produce 80 kilograms. And I can also here use, for example, 189 centimeter, and it will parse it as 189 centimeter and do the calculation. But you see here, you can mix the units and start to do funky stuff. And you see also that, for example, for that BMI index, that the number has to be scaled up if you're using centimeter or something. If you would have used centimeter all the way up, you see you get kilogram per square centimeter, but then you have to rescale that number if you want to use it to compare whether I'm in the safe zone or not. But as far as the calculations being done, that is taken care of by the reference library.
Do those two values compare equal?
Yes. I will come back to that, but they will. Not equal, equivalent.
Can you convert one of those values to the other?
Um,
I suppose we do a cast.
Yeah, you can. So you can take, for example, kilogram per square centimeter and ask what the value would be when expressed as a kilogram per square meter. Yeah. Yeah, and you can read it from the command line. I'm not just going to skip that. So let's talk about units. These are the base units: the meter, the second, the kilogram, the ampere, the Kelvin, the mole, which is the amount of substance, and the candela, which is the unit for light, for luminosity. So these are the 7 base units. But you can also derive units. For example, for speed, you have meter per second, and for acceleration, meter per square second. There are also some units, when you think of them, are also derived units. For example, the unit for the angle, rad, which is actually meter per meter. Because if you think of it, when you express an angle, that's actually the distance on the arc divided by the radius of that arc. So it's a meter per meter. And then frequency is hertz, which is per second. Then you have, of course, Newton, which is kilogram times meter per square second. And then you have a special one, the degree Celsius, which is actually Kelvin shifted, not multiplied, shift by 273.15. And then you have multiples. So you have kilo, so you go from meter to kilometer. Then you have, for example, millisecond. This is a thousandth of a second. But then you have something like, for example, a megameter. Yesterday I traveled 1.6 megameter. Yeah. And a kilosecond, what's that? Turns out, when you think of it, 1 hour is 3.6 kiloseconds. But if I say, yeah, come back in 1 kilosecond, nobody will know what I mean. So there you have it already. There are some things with SI that are not so straightforward. So, yeah, you have the seconds, megameters, megagram. Yeah. For some reason, we try to be rational as human beings and set up a system that this is going to be rational, and then we say millions of kilometers. Doesn't really make sense if you think of it. So, in order to not have all that kilogram per square meter thing going on for expressing a BMI, let's define a BMI unit in a program, then convert the quantity before we output it. So that would be like defining a Newton for a force, and then using that instead of using the base units. So this is all you have to do. Well, no, this is the first step. You have to define BMI as a quantity, as a quantity type. And if you use the S-type BMI class, when you do the calculation, you can actually continue to use the result as a BMI quantity so that you get all the typing in place in Java. And so just that part is nothing more than just defining an interface which extends the quantity BMI, and then you can have all typing done for you so that you are sure that at compile time you already have some things in place so that you're not dividing, for example, the height by the square of the mass, because that wouldn't work.
What will happen if I forget to write this one divider? I will do only once, for example.
Yeah. So let's see what happens. I don't think it says something special over here yet. No, that's right. But the next step is a bit more interesting, because then we're actually going to use the unit B. I just used B with the stroke to have some more fun. Define it as a unit for the BMI quantity. And then, so all you have to do is to say that that new unit, the BMI unit, is a kilogram divided by the square of a meter. And I assign the B sign to it. And then before I output, I can convert it to that unit so that I'm sure that I get it in the right units, the one that I want. And I'm just going to change this so that I don't have to go. For example, like this. Now you see I get the 22.4 in that unit. So I start with 80 kilograms, 189 meters, and when I just do the calculation and output it straight away, I get kilograms per square meter. If I convert it to B, I also get 22.4. If I, however, change this one and I say I express it as a centimeter, you see that it's scaled to kilograms per meter, per square meter automatically. And if I forget to divide 2 times, when you try to cast it to that new unit, it will say, oh, kilogram per meters. That doesn't work out as a BMI unit. It has to be kilogram per square meter. So then I get the incommensurable exception. And it's actually smart enough to say, I think, kilogram per centimeter is not compatible. So you actually get information. There's a meter missing there. The nice thing is, with all the trouble I had with the sound, all my demonstrations are going to perfect this time. That's good. Dimensions. So these are the base dimensions. So they reflect what we had in the base units. So you have the length, the time, the mass, and the electrical current. Thermodynamic temperature, amount of substance, luminous intensity, and then we also need one. Like, for example, for the angle, we need to be able to handle that too. So that's basically a software thing. You have to handle absence of dimension too. And then for the force, if you would ask, for example, the unit Newton, what kind of dimensions are you built up of? It will reply something like L times M times T minus 2. So what you can use this for is to auto-detect if you say that you have from a command, if you're reading the quantities from the command line and you don't want to say to your user you have to put the mass first and the height afterwards. You won't have to say, you can just put in a length and a mass in the order you want to. You can detect automatically which dimension these quantities have and then do the calculations according to the dimension. So it's easier to understand when I show it. So for this little program, I just read the first quantity and I read the second quantity. And then I say I reserve a property mass and height. And I just go and read the dimension of the unit of the first quantity and I read the dimension of the unit of the second quantity. And then I know I can compare straight to, for example, the dimension mass. An alternative would have been to ask, for example, for the base unit and then check that it is a meter, except if I would be working in another system, maybe the meter is not the base unit for length, but in all systems of unit, the dimension mass is the dimension mass. So that's a safe way to detect whether something is a length or a mass or something else. Then you can just make sure that you have one mass, one length, and do the calculation, and everything works out fine. So just to show. There you go, it does a calculation, 22.4. And if I switch everything, and express it in centimeters, it all the text does a calculation, and I still get 22.4 as the BMI.
Question, you mentioned different systems and the base unit for the system that you're working in. If the user had entered something in pounds or something in feet and inches, would it automatically, convert to the right system, or do you have to be explicit about that?
The quantity will have the unit that you expressed it in. If you ask for the base unit, I think you can get a different unit depending on which system. I haven't tried that, I'm not sure about it, but the dimension will always be the same. So if you ask the unit which dimension it has, that will always be the same.
Can you put inch there instead of centimeter?
I can try. I'm not sure how that would go. Because I don't think I have sent it up. No, it's not recognized. So I haven't set up that system already. Yeah, you have to configure it, yeah. Just some notes on doing the math. So we already have divided and multiplied, but there is more stuff to it. Actually, we can start with equality and equivalence. So obviously, if you look at the units, a kilo ohm and a millihertz are not the same thing. And a kilo ohm and a milliohm are also different. But a kilo ohm and a kilo ohm, they are equal. But the Newton and a kilogram times meter per square second, they're not equal, they're equivalent. And then they have things like, for example, the kilogram per square meter is equivalent to milligrams per square millimeter. But here we already have a thing like, should you have a function to normalize expressions into what would be something closer to the base unit? That's something you could consider, and also for quantities, for example, that 1 milligram per square millimeter is automatically normalized to 1 kilogram per square meter, but there may be contexts where it makes more sense to express a quantity as milligrams per square millimeter. For example, maybe for some special paint that is for small devices, people may probably think more in terms of milligrams and millimeters and not of kilograms per square meters. So that's just to get the reference in people's head correct. So the same for quantities. A kilo ohm is obviously not the same as 1 millihertz, and a kilo ohm is also not the same as 1 milliohm, but 1 kilo ohm and 1 kilo ohm, they are equal, and 1 Newton and 1 kilogram times meter per square second, they are equivalent. But here you also have that 1 kilo ohm is equivalent to 1000 ohms. So it's not just comparing the values and the units, you have to convert into one unit and then do the comparison in one reference unit. Then you can add, for example, 1 ohm plus 1 ohm is 2 ohm. And then if there's something you have to think about, if you get, for example, 1 ohm plus 1 milliohm, should you express it in ohms or milliohms? And what we decided is that we use the first unit if we can. If it leads to overflow, you can fall back to the second unit, and otherwise, if it leads to overflow in both units, you just throw an overflow error. So 1 ohm plus 1 milliohm is 1.001 ohm, whereas 1 milliohm plus 1 ohm leads to 1001 milliohms. And obviously, 1 ohm and 1 meter, that does not compute. Question: how much is 0 degrees Celsius plus 0 degrees Celsius? Normally, I would have said, well, that's easy, 0 degrees Celsius. Except if somebody in the presentation asks for it, I would immediately reflect it's probably not going to be 0 degrees Celsius, unless the guy points out that he's doing a presentation asking the question, in which case I would be thinking, yeah, maybe it is 0 degrees Celsius. Maybe it could be 0 degrees Celsius. On second thought. And on third thought, you had, I heard you say it, 273.15 degrees Celsius. Okay.
Should you be
Who?
able to add temperatures?
Yeah, there may be, for example, with thermodynamic formulas, temperatures be included. So it actually makes sense. I thought to start with that doesn't make sense, adding 2 temperatures, but temperature is actually equivalent to, that's an amount of energy, and there are thermodynamic things where you want to add temperatures actually. So who in this room says it's 0 degrees Celsius? A couple of people, yeah. Who thinks it's 273.15? Also a couple of people. It's like, don't compute. And there are like, it's like 1/3, and then 1/3 not really knowing. That's like the Brexit in the House of Commons. Yeah.
We ask for an extension.
Yeah, we ask for an extension, right? Well, actually, all 3. Because if you're dealing with 2 absolute temperatures, then 0 degrees Celsius means 273.15 Kelvin. And when you do the calculation, it's 546.30 Kelvin, which goes back to 273.15 degrees Celsius. However, if you're dealing with 1 absolute temperature and 1 temperature change, then 0 degrees Celsius as a temperature change is the same as 0 Kelvin, which means that the end result is 0 degrees Celsius. Or you could be dealing with 2 temperature changes, in which case both of them are 0 Kelvin, and the result is 0 Kelvin or 0 degrees Celsius. So, all 3 answers are correct depending on the situation. And that's something that we discovered as part of working on this, that when we started working on this library, we didn't have a concept of, is this quantity an absolute quantity or a relative quantity?
Ratio or interval scale.
Yes. And that's something we hadn't modeled. And then I go back to my question in the beginning, are you a domain expert in your system, right? Do you really know the SI system that well that you can write a library to handle all this stuff?
Nothing to do with SI. It's just ratio versus interval.
Yeah, sure, but why are we using degrees Celsius? Because this causes a lot of trouble, right? It's easier for us because we get the scale from 0 to 100 instead of 273.15 to 373.15, so that's a lot of trouble. But degrees Celsius is not such a nice unit of measurement to work with. And I was at Java Zone at the end of last year, or in September last year, And there was actually somebody also complaining about time. So if you can go on Java Zone and watch that talk, it's a very good talk about all the trouble with daylight saving times and all the troubles you can have there. And then she had a slide like you have also the formatting problem, where in the US they do month first and then the day and then the year. And then she had also a slide saying, and these are the countries using Fahrenheit, and these are the countries using Celsius, where a punchline was, of course, using degrees Celsius. That's the rational thing to do. But then you have things like this, right? I'm not done with degrees Celsius. I'll come back to it because there's more. Multiplication. We already did that, and division also. So kilograms times a meter is kilograms meter. And you can, of course, multiply a kilogram with a millimeter and a gram with a kilometer. And then you have, okay, should you just continue to use gram times kilometer, or should you reverse it into kilograms times a meter? And then you have a meter times a meter is a square meter, and a kilometer times a kilometer is a square kilometer. What about a millimeter times a kilometer? Should you automatically convert it into a square meter, or stay with a millimeter times a kilometer? And what with, for example, a micrometer times a meter? Should you then automatically change it into a square millimeter? That there may be good reasons to do that, and there may be good reasons not to do that, because there may be something that actually makes sense to be expressed as a micrometer times a meter. Quantities, however, are straightforward. You just multiply the value and you multiply the units. So the only problem is with the units that can have strange effects. Division. Also okay, but then up to here, that's okay. If you divide a kilogram by a meter, you get a kilogram per meter, or you get a kilogram per millimeter if you divide by a millimeter. Maybe you should convert, maybe not, if you divide a gram by a millimeter. But then you have troubles like, for example, a square meter divided by a meter, that's a meter. But a meter divided by a meter, that's something without a unit. You can divide a kilometer by a kilometer, but what if you have a kilometer divided by a meter? Is that 1 kilo? Something to think about. Quantities, again, that's easy. The trouble is in expressing the unit. Then you have powers. The square of a meter is a square meter. The square of a square meter is the meter to the fourth. And same for quantities, it's just basically like a multiplication. So once you have worked out how to take the power of a unit, you can do it for a quantity too. A square Kelvin, that's okay, but a square degree Celsius, what's that? Yeah. And then you have, of course, a meter times a degree Celsius. Is that like a meter times a Kelvin minus 273.15? And what does a square, what does 0 degrees Celsius to the second power, what does that mean? Is that maybe 74,610 square Kelvin? So, and then back to Celsius, yeah? So Celsius is not a good unit to work with. But you may have things like, for example, if you're dealing with isolation material, you may, for example, have that some piece of material can hold, for example, 5 degrees Celsius per meter, right? So there is actually use for using either degrees Celsius or perhaps better Kelvin as part of such a calculation.
Because that's delta.
Yeah, if it's a temperature, yeah, for an isolation material, it would be the temperature change, which would be degrees Celsius, yeah.
Then delta Celsius is delta Kelvin.
Yes, yes, that's the same thing. Another thing, we discussed degrees Celsius. What about a millidegree Celsius? Is that 1 millikelvin, or is that 273.151 Kelvin? It turns out it's always 1 millikelvin, because the milli, the prefix, makes it always a change. It doesn't make sense to convert 1 millidegree Celsius to 273.151 Kelvin. Yeah, why not? Good question, and that's why I say SI, that system of unit, there are some peculiarities that maybe don't make much sense, but once you use, for example, milli or micro or kilo in front of a degree Celsius, the additional shift operation disappears and it becomes the same as a Kelvin. Parsing units and quantities. Speed of light. These are a whole set of ways to express the speed of light, and these are the things you have to be able to handle if you make a library. Ideally, you have to be able to handle them. And you can have like m/s, and with 1,000 separators and without 1,000 separators, or you can use it in kilometers per second, and you have to be able to handle the decimal point, and 1,000 separator. Or some people may actually want to use the star, or they may want to use the times character from Unicode, or they may use the middle dot for the multiplication, and they may use -1 with the sub in HTML, or they may actually use the Unicode Unicode minus and 1 characters, or they may want to use the caret to express the power. And you have to, of course, to be able to handle not just seconds, but also the hours. And then you have local representations of the hour. For example, in Norwegian, 1 hour is en time, so they would use a T. When I tried this out for the Norwegian conference, I figured out that this actually parses as kilometers per ton. I had almost included it as something that worked out until I figured out no, it doesn't. And then you have miles per hour. So there is not even a slash or anything. It's actually the P that says that's a per hour. You also have to be able to handle that. And then you have, of course, the whole systems of measurement thing. You want the metric system, meter and kilograms, seconds and amperes, and you want the imperial system. And then you want to be able to define things like the United States customary units. You want to have horsepowers. I think horsepowers in the US is different from the imperial system. There is one unit there that has the same name, but is actually slightly different. Or a gallon? Yeah, gallon, right. So that makes it even more complicated, of course. Maybe you want to define the Roman units of measurement, and maybe you want to have Norwegian units with all the funny signs and everything, if for some reason you would want to have that. But let's get back to the original problem. Primitive Java types are primitive types. So they're not good enough to really represent quantities. And when you looked at the examples, it's not so difficult once you have included the dependency in your POM file to just use quantities and do the maths with it. And it's probably simpler because you don't have to convert manually from kilometers per hour to meter per second or whatever. Yeah. A little bit about JSR-385 status. Those few Java developers that were in the room can have a look at it and also look at the GitHub repository, look at the code there. I'm not sure whether you only use and have talks about boost units, but if you are a contributor there, you may want to look at our source code, of course. The current status is that we are in an early draft review, and we hope to launch about the same time as the new SI system will be launched. And we're preparing for public review and public review ballot. Maybe not so relevant for C and C++ developers, but JCP is an initiative to let developers, Java developers from all over the world to contribute to the Java programming language. I started out with just sending out a pull request to fix a link in the README file on GitHub, and then fixed a Java doc comment, and then started writing some unit tests, and now I'm presenting here in Bristol and actually have to worry that the Brexit maybe matters to me too. So that's how it can go if you start working on open source project. But yeah, it's very interesting, and the people are very welcoming and helping. So that's a very good experience. So whatever programming language you're working in, contributing to open source is a very positive experience. If you would want to become a JCP member, it's actually easy. It's for free. So that's not a problem. And I suppose that in most other languages, contributing to official standards is also something that is very welcomed. I know that from the ACCU conferences I've been to, that contributing to C and C++ standards is something that you are involved in. That's not so relevant. I also want to say a few words about other programming languages. The way it is handled is often, it's very, it reflects well how the programming language behaves and how its developers behave. So for Java, it's not a strange thing that it ends up as a JSR and is included in the programming language in the end, maybe 20 years too late, but at least it happens. So it's not a surprise that there is a boost units library for C and C++. But if you look at other programming languages, like for example Python, I did a look and I didn't find one reference library, but like 1,000 libraries that do all sorts of strange things in varying orders, some of them just holding a value and a unit represented as a string. So that's very typical of Python. Same for Ruby, I found a couple of gems, but not really doing what they should be doing. I also tried to look up a JavaScript library, and that was like, yeah, a Newton. So you see what kind of developers you have. I don't know whether there are JavaScript developers in this room, but they are very much front-end focused and you know, heavy stuff like kilo ohms. That's not really their thing. Yeah, exactly. They already have to do enough with the numbers. Are there any more questions or comments? Yes?
The original orbiter problem, was it across a calling interface or across a data bus interface? The part that sent it and received the value?
Yeah, it would.
I recall it was a communication interface, not a calling within one application.
Yeah, so it was between two modules, and one module developed by Lockheed Martin and the other one by NASA.
Was it running on the same computing platform, or was it communicating over data bus?
Oh, I'm not in the detail. No, I don't know.
If it's over a data bus, then using a unit library wouldn't solve it.
Yes,
You wouldn't include the unit in your data communication. That would be 100% overhead or something. You never get it.
Yeah, well, that depends. If, like you saw here, if you print a string, if you print a quantity as a string, the unit is included. So if that would have been sent over the wire with, for example, meter or Newton, it would have been parsed as meter and would have been handled correctly.
Yeah, but wire bandwidth is always scarce.
Yes.
It would be 100% overhead. You would never get it through.
Yeah, but that would be an optimization that would maybe be premature and catastrophic.
Yeah.
So So cutting away the meter or the newton or the unit just to save some space and bandwidth, that's a risky thing to do. So that's something you would have to consider carefully. But like NASA pointed out, it was in the specification, so they should have used newtons, or they should have, but once it was wrong, NASA should have been able to find it and correct it. So there are many things that went wrong in there. But when you use these quantities and you, for example, include them in JSON or XML, you should not just extract the value, but actually format, also do the whole quantity and not throw away the unit, because then, of course, you're back to the same original problem. You have internal conversion and handling of quantities, but once you communicate to the outer world, you suddenly are back to primitive types, and that's not a good way to do it.
Anyway, the communication, this communication library interface should use units, and in such cases, like quantities, and there will have conversion to the default quantity used on the interface, so it will solve the problem too.
If you over data bus.
Yeah, but you have some interface to send messages over data bus, and then input should be in quantities, not as numbers.
Yes, yes. So, yes, so all the communication should have included the unit as part of the quantity representation. Yes. We can talk about it later, yeah, but yeah. Any other questions or comments? Yes. Oh, sorry?
Another question, I contribute a bit of human sensor for everybody's use. In the marine field, there are sensible organisations measure grid position in meters, and they measure depth in meters, and it's nice and easy. But there are certain organisations on the other side of the Atlantic that measure grid position in US survey feet and depth in international feet, which is great until you want to work out the range from the surface to something down there.
Yeah. Okay then, thank you.